Hey guys, welcome to episode 2 of my Explaining CPU Architecture series. This time it's going to again be a little bit of a long video, shouldn't be as long as before. Gonna try to run through this. It's basic stuff again. Most modern CPUs made today have all this stuff. We have to go through the basic stuff to get to the really good stuff. You have to learn this stuff the right way. You gotta learn the basics and then build on that. Okay, so we're not going to be digging into super interesting stuff, well, it is interesting, but we're not going to be digging into the super complicated recent stuff until we get the foundations down. We'll get there soon, but for now, gotta learn the basics. Okay, 4 things we're going to be learning today: pipeline stages, pipelining, superscalar architectures, and in order and out of order processing. The first 3, all modern CPUs have, period. Last one, 95, I don't know, pretty much almost all of them have it. Let's get to it. Last episode, we learned about the machine cycle. Every CPU has it, it's just a fundamental thing. It's just how a CPU works. It has to go through these stages to work. Pipeline stages is like another way of saying the machine cycle. The machine cycle has 4 steps. We're just going to use a different word now. We're going to use pipeline stages. Imagine this as a pipeline. A line that the instructions follow to be completed. Pipeline stages is how many stages are in that pipeline to be completed. Now, logistically, as a human, you would say there's 4 steps, and if you're running at 4 hertz, and all of these stages are of equal importance, and you need them all to work, it would take 4 seconds to finish. Now, what pipeline stages as a concept is breaking that apart, basically. Even though there's 4 fundamental steps to a CPU, and they're all of equal importance, they don't all take the same time. Some of them are simpler than others. Some of them are electrically bigger than others. Some of them take more time logistically than others. So even though as a human you would think fetch would take 1 stage, decode 1 stage, execute 1 stage, store 1 stage, 4 stages, 4 steps, 4 seconds at 1 hertz. Cool. How it actually is though, it's a lot more complicated. When you look up the pipeline stages of a CPU, you will get the best case scenario, how many stages an instruction will take to get through the architecture to be completed from start to finish. A CPU may have something like, for example, 17 stages. So it's basically these 4 basic steps broken down into more simpler steps, and it's 17 is a step. So basically, every single clock rate, in the best case scenario, it'll take 17 clock cycles to get from beginning to end. In reality though, there's different types of instructions that take longer in particular stages to get through. Sometimes resources take longer to get ready for an instruction than the pipeline stages that are in the CPU. Basically, the main thing to learn about pipeline stages is a CPU is broken down into many simpler stages than just 4, and these stages can individually take longer or shorter time depending on the type of instruction being issued, the load on the CPU, the technologies that are in the CPU, many things affect it. Main thing to take away from it is the machine cycle can be broken down into a lot simpler steps, more of these steps, but they're simpler, and they can all take a variable amount of time. Next thing to move on to, let me get to a quick note. It is said that a CPU with more stages than another will be able to clock higher. This is logistically true. It's not always true, but it's by logic true because you're breaking down those 4 fundamental steps into even smaller steps. So you have more steps, but you have smaller ones so you can get through them faster. But let's say you run at 4 hertz and you have 8 steps, you're going to get everything done in the exact same time as if you had 16 steps and you ran at 8 hertz. So you can run faster with more steps or more stages, more pipeline stages, but you get less done per stage. So it's kind of all proportional. That's the main thing to take away from that particular note, that across designs, the more stages you have, logistically, the faster you can run, but you get less done per clock cycle. So it's, you know, it's an important concept to get, not something that you should use as a base of comparison. Pipelining, next instruction, or not instruction, sorry. Next technology, or really the first technology that's really introduced in this episode. Pipeline stages, everything has it. It's just fundamentally what makes up a CPU. Pipelining, however, is a technology. Now, as an instruction goes to, let me restart. Let's say you have 4 instructions. In a non-pipeline CPU, that first instruction would go to the fetch stage. It would go to the decode stage, it would go to the execute stage, and go to the fetch stage, and then be done. The second instruction would not go until that first instruction has passed from beginning to end of the CPU. It's like having a hallway. It's like having 4 people who want to go across a hallway, and you're in a line. Even though you logistically, or it would make sense for you to all go at one time in like single file order down the hallway, it would basically be the first person goes, and once they reach the end of the hallway, then the second person go, reach the end of the hallway, then the third, start, finish, fourth, start, finish. That's very inefficient, because that one instruction could be in the execute step, and store will be doing nothing, decode will be doing nothing, and fetch will be doing nothing. By the way, FDES is just, you know, it's easier to identify than reading fetch, decode, execute, and store in very small letters. Now, what pipelining does is it makes use of the full CPU, or at least as much of the CPU as possible, at all times. Now, there's this little kind of chart here. These X's are basically meaning empty. So let's say you just turned on your CPU and you have 4 instructions right away. And you get issued the first one, the second one, the third one, the fourth one. The first one, sorry, and let's also clarify that each step can only handle 1 instruction at once. The first instruction, first clock rate, or first clock cycle will go into the fetch stage. Decode is empty, execute is empty, store is empty. Second clock cycle. This one will move over to the decode, and the second instruction will get to fetch. Execute empty, store empty. Next clock cycle. The first one has moved on to execute, second one to decode, third one is loaded in, store is empty, and the fourth clock cycle, store is being, or the first instruction is already on store, second on execute, the third is on decode, the fourth one is on fetch, and as you can guess it, in the next clock cycle, 1 will be done, 2 is at store, everything will move over, and everything will be busy, it'll keep going like a pipeline, like an assembly line in a factory. It's every single part of the factory or the pipeline will be working at all times. It's the most efficient this way. All modern CPUs have it, and it's really cool for performance. That's the main concept, basically. Next one, and this is, I just kind of weirdly, this is one of the most important concepts to understand. Superscalar architectures. You can't really read this, I apologize, but it says superscalar architectures. This concept here, get this, because this is not only kind of interesting, but it's very important to understand. So, we're familiar with our F, our fetch, our D, our decode, our E, our executes, and our S, our stores. Correct. Now I just added in a little thing called the scheduler here. Schedulers are found in almost all modern CPUs, and they're very complicated, but for now we're just going to act as if it were a queue or a line, somewhere that holds instructions until they're ready to go to the next step. For now, let's just leave it at that. So let's say you have 2 instructions, and let's say the fetch and the decode can only handle 1 instruction at once. The scheduler can hold 2. Remember, to us it's a queue, a line. It will hold 2 as a capacity for 2. And if you notice, there's 2 execute units here, and there's 2 store units here, and they can each handle 1 at a time. So you can probably tell where I'm going with this. First instruction goes through. It goes to fetch. It's done. It goes to decode. The second one goes to fetch. We're using pipelining, by the way. It goes to fetch. Next clock cycle, the first instruction goes to the scheduler. Let's say it's a pretty big instruction, and it has to wait a long time for the resources it needs to execute to get there. next clock cycle. Let's say the first one's still waiting. Second one loads into the scheduler. They're both waiting in that line. Let's say next clock cycle happens. Let's say they're both ready to go. Now, let's say we didn't have a superscalar architecture, meaning we didn't have multiple execution or store, or we didn't have multiple units. We only had one slot, or the capacity for one instruction per stage in our pipeline. Basically, you would have to let the first instruction go, and the second one would have to wait until the first instruction is done. What Superscalar architecture does is make a duplication of another resource, and now you can handle twice the capacity. And if you make a third one, you can handle 3 times the capacity of that stage. Fourth one, 4 times the capacity. So let's keep going with our little example. Let's say you have 2 instructions and they're both waiting on the scheduler. They're both ready to go. Now you have 2 execution units. You can execute 2 things at the same time. You can do 2 things in the time it takes to do 1. Sure, you have to do double the resources, but the beauty of it is it's twice the performance. So the first one, it's ready. It'll go to the first execution unit. The second one, it's ready. It'll go to the second execution unit. Let's say next clock cycle, they're both done, and there's 2 store units here conveniently. And the first one will go to the store unit, the second one will go to the second store unit. The main point to get away from superscalar architectures is basically, I'm really sorry for being like floating in and off screen, it's just I have to get all this on camera. Main thing to get away from this, it's everything operates off the machine cycle, but there are queues in a CPU. There's more complicated parts of the CPU that can go into a CPU to make better use, not only make better use of the resources that are there, but also there can be multiple of those resources, multiple iterations of the machine cycle going on in a core at once. You can have multiple instructions be in the same stage at once at multiple places. You could have, like, let's say you had several fetch units, several decode units, a big scheduler, and several executions, several stages. You could have tons of instructions going around the entire CPU at once. That's kind of, when you think about it, it's like, wow. If you get a lot of units in there, you can get a lot of work done. And that's how modern CPUs are. You have very big fetch units, a lot of decoders, very, very big schedulers, a lot of execution units, and very big store units. You can do a lot of work at once per clock cycle in modern architectures because they basically didn't keep the capacity locked at 1, where if you're fetching something, it's 1 instruction at a time, no more. They said, okay, we'll do 2, 3, 4. Decode, we can decode 4. We can do more than 4 instructions at once now. Scheduler is going to hold tons of instructions at once. Execution units, we can have tons of things executing at once and tons of things storing at once. It's all based off the very basic machine cycle, but it's really cool to think that you can just duplicate the resources to make a much better CPU, much higher performing CPU. That's the main thing to get away from it. Sorry, I really like this concept and it's very important to get. Last one for today. It's been a long video, but it's almost done. In order and out of order processing. It sounds easy to get, and it is. It's just the concept kind of takes a second to click. In order processing. Let's say again you have 2 instructions. For now, let's just go back to the very simple one. Just to the simple, 1 instruction at a time, except we're going to add it in a scheduler. We're just going to add it in a queue. So basically, let's pretend we're doing this. We have our scheduler, and it can hold 2 instructions, but we only have 1 execution in it, 1 instruction at a time. We only have 1 store unit, 1 store unit at a time. Or you can only store 1 instruction at a time. I can't talk today. So let's say in an in-order architecture, you would have your first instruction go in, it would go to the next stage, second would come in, it would go to the next stage, and keep on going, and it would get to the scheduler. Let's say the first instruction is very complicated, and let's say the second instruction is very simple. It can be done quickly. The first one cannot be done quickly. In an in-order CPU, basically the first instruction would get to the scheduler, and it wouldn't be ready for execution for a long time. The second one would get to the scheduler, and even if it were ready before the first one was ready to go, it wouldn't go. In order is first in, first out. If the instruction gets there first, it's first out. It doesn't matter how long that instruction takes, how complicated it is, how much it holds up the CPU. It is the first one in there, it will be the first one out. That sounds inefficient because it is. You could have an instruction be very complicated and hold up the rest of the CPU. So what they did, and this is pretty much on all CPUs now, out of order execution, you can still get, I'm pretty sure the newest Atom line, some parts, the SIM cluster of the CPU is still in order, but it doesn't impact performance that much in this implementation. Anyways, what out of order is basically, let's have the exact same kind of cycle again, the same units again, and let's say you get up to the scheduler again, you have both in the scheduler. Out of order is first ready, first out. So the second instruction is simple. It's ready right away. When it hits the scheduler, a couple clock cycles later, it has the resources it needs. It doesn't matter whether the first one is ready or not. It goes. Okay? That's the concept basically. You know, if whatever is ready, it'll keep going. It doesn't matter what came before it, doesn't matter what came after it. Whatever is ready will get pushed through the architecture. The only caveat is dependencies. And an example of dependencies would be like, let's say you have two instructions, A plus B equals C, and C plus D equals E. You obviously can't do the second instruction until you finish the first because you don't have C, you don't have the result. That's the only real case where you have to wait for past instruction to be done because you need a resource from the previous instruction. So that is essentially out of order processing. First ready, first out. If you're ready, keep going. If you're not dependent on a previous instruction, keep going. And yeah. So today we learned, sort of abruptly stopped, but yeah, that's the concept basically. Today we learned pipeline stages, all CPUs have them, pipelining, technology that all modern CPUs have, superscalar architectures, again, same thing, almost all of them have it, or all of them have it, and in order and out of order processing, most modern processors have it. So, yep, that's the second episode. Hopefully you learned quite a bit. It's again simple concepts. We're not going to be getting into anything too complicated, at least for a couple more episodes. But very soon we're going to be getting into recent stuff where you'll be able to learn stuff about technology that you might be holding in your hand or using on your computer. So, you know, we're on the way to more complicated stuff. And if you like everything so far, you know, I'd love to get some feedback, get some improvements. And yeah, I hope you've been liking it so far. So, thank you for watching, and I hope you learned a lot. Ciao!